So this morning's lecture is going to be on big O notation. And big O notation is basically it's like how efficient does your algorithm run? Like how well does everything work together? Is it going to be slow? Is it going to take a lot of memory? Is it going to take a small bit of memory? And that's like the way that we have to think about our algorithms at all given times. So the benchmarking code is basically the act of timing your code. How long will that particular bit of code take to execute? And basically what we're doing is we're trying to see, is your code slow? If it's slow, how do we improve the speed? As of right now, we're just working about making our code work. I fully understand that we're still learning the language, and the way my boss always put it was, make it work, then make it fast. First things first, just make it work. Get something out the door. Like, you just need something to work. Then after you demonstrate that it works, then at that point you can make it fast. If your code is slow, and eventually, like, the code that you write continuously is not very efficient or anything like that, you're basically asking your users to move away from your site or to go to another page. Can anybody guess the threshold of patience that people have for the internet and how long things take to load?
5 seconds.
5 seconds. Anybody else?
3 seconds.
2. So it's 2 seconds. If your site takes longer than 2 seconds to load, they say generally people are like, they get a little bit frustrated with it. They're like, this site's not working, and they'll go somewhere else. So you have less than 2 seconds to actually make people want to stay on your site, to get everything loaded in. And that's why we need to write the code to be as efficient as possible. Right now, your code's only handling like maybe 1 or 2 people using it at any given time. But especially once you get to like thousands of users and things like that, if you have one piece of code that relies on another, then you need to have code that's super, super fast. So how does that apply to us? When we write algorithms, when we write code, when we write the methods within our giant classes, we want to have our algorithms and code as fast as possible, code that uses as little memory as possible. And if you write bad code all the time, then you're basically asking somebody to move away from your site. Also, it's very, very important during interviews when people start asking you, like, what's the big O notation on this particular algorithm, then you can be able to speak to it. So I've got a little bit of code here, and I've dropped it in its place over here. So let's read through it line by line. Line 1, require benchmark. Require means that I'm bringing in an external library, something that's available to every single Ruby class, but not specifically in another file. You can kind of see this capital B benchmark on line 13. That's a class that I'm going to be using. So I have this benchmark. I'm bringing in the library, and I have 2 methods. The first one is just print hi. And all it does is it puts it out to the screen, just this string hello. Then I have something that says repeat times with a number. So you pass in some sort of number, let's say it's 10. 10 times do puts hi. Which one is going to be more efficient? Should be fairly obvious. Just the first one, because I only have to print it 1 time. This one, I'm not sure how many times I need to print it. It should increase the amount of time, like the amount of time that it takes to execute will increase based on what I say the number is. So I'm going to benchmark this 20 times and just say, like, how long does the first one take to print, and how much time does it take the second method to execute over here? And I'm just calling it down here under time. So I'm just going to run, where is everything? Ruby benchmark.rb, and you can kind of see. So the first one I printed out once, and the second one I executed it 50 times. I'm still calling just one method, but this prints it out 1 time. The other one prints it out 50 times. Hey, Chris. You can kind of see at the very top, I have the print hi method, and the amount of time that it takes to execute is 0.000138 seconds. So it's still a fraction of a second, so it's fast. When you go further down, you can see that this one takes 0.00452. So it takes roughly around 3 times the amount of time to execute this particular bit of code, despite it printing out 50 times. So one thing I'm just printing out hi 1 time takes 0.00138. The other one, when I print it 50 times, it increases the amount of time and the amount of memory that it's going to take to execute this particular bit of code. Yeah.
What were the other numbers before that, like the first two?
The first two numbers, it goes how long, I'm guessing this is basically how long does it take the user to actually hit this one. This, how long does it take the system to execute it, and then total, how long does it take between those two things to run. I'm not exactly sure what this is. When we jump back over here, I wanted to show off a quick visualization of different benchmarking resources. Again, you can read all the different things that Benchmark can do over here on the Ruby docs. But when I say that you can do any number of sorting algorithms, remember the other day we had Tristan doing a sorting algorithm. There's all different types of sorts. And I'm not going to play through this entire 4-minute and 25-second video, but you can kind of see these are different examples of the different sorts that we have. Selection sort, shell sort, heap sort, quick sort, bubble sort, which is one that I believe we had a challenge on that. And you can kind of see that when we have things of all different lengths and we wanted to have to more or less look like a graph, a linear graph going upwards, how long it's going to take. So I'm just going to play this for a little bit. So you can kind of see that like different algorithms that you write have different different speeds that they execute. You saw this this quick sort, and I think the merge sort finished first, whereas like the selection sort is still going. The bubble sort is still going because it's not the most efficient code that you could possibly write. So it's just kind of like an interesting visualization for you to have. So let's jump over into Big O. Big O is absolutely crucial in terms of like understanding how efficiently your algorithms run, both in terms of if you're writing larger scale applications and especially when you're interviewing for jobs when they ask you, so what's the Big O notation on this particular algorithm that you've written over here? Big O is the complexity of your function, the O, like how complex your function is compared to the input size, which is your n. Again, Big O, the complexity of your function, which is that O, in terms of input size, which is the n. In layman's terms, it's how long does it take your code to run? How complex is the code that you've written? There's different Big O, like more or less rankings, I would say. So when we do O of 1, it's a happy face. Like this person's just kind of chilling over here, this little emoji here. The speed that your code runs doesn't depend at all on the size of the data set. So when we take a look at the code that we had a little bit earlier, it looks like all this method is doing is just printing the word high. I don't care what the input size is, it's just doing one thing and that thing is doing high. It doesn't matter what your input is, it's just doing high. You can pass in 1,000 different arguments, but all it's doing is printing high. And because this is going to be a constant every single time, it's going to be your O of 1. Then the next most efficient one is going to be O log of n, which means that if you have 1 time to 10 times the amount of data, it takes twice the amount of time. O of n is what we have over here for that print it 50 times, which means that based off of the data set that you provided, that's the amount of time that's going to take to execute more and more. So the larger your data set, the more time it's going to take, kind of like this repeat number. So if I repeat it 1 time, that's going to take a shorter amount of time than when I do repeat it 50 times. Then we have O n log of n, which means around 10 times the amount of data is going to take 20 more times. This O n squared means that 10 times the amount of data is going to take 100 more times. This is when you have loops within loops. So if you have a loop with an array of 10 things and an array of another 10 things, and you need to do a loop within a loop, since that's executing 100 times, this O n squared. And then this one I've never really seen, O2n, I've actually never seen that. I'm not sure. So again, the big things that you need to know are like O of 1 is constant time. So if you pass in 1,000,000 arguments or 1 argument, it's all going to be the same. So let's say that we have a method called first element is red, question mark. The question mark means that we know it's going to return true or false. And we provide it some sort of an array. That array can be one thing, could be 10,000 or 10 million things. It doesn't matter, because inside of here, I'm basically just seeing, is the first thing red? And if so, I'm going to return true. Otherwise, I'm going to return false. Have people seen this particular way of writing code before?
Yeah, I saw that on Stack Overflow.
Okay. What is this? What type of code is this? It's a ternary operator. So the way that it reads is this question mark is an if. So you can translate every time you see the question mark to equal an if. So if this particular thing, then return this first half of the colon. Otherwise, do the other half of this. Is there a way I can just refactor it even more than this?
Just take out the ternary and return false.
Yeah, I could just get rid of this whole thing altogether. Array of 0, so the first thing is, does that equal red? It's going to return me true or false by default, so I don't actually need this second half. So a real life example of O of 1 in terms of constant time is that there was a village in Africa that's really complained about their internet being slow. They said, our internet is so slow that I guarantee you I can put a bunch of data inside of a carrier pigeon's leg, and then I can get that to a town 50 miles away faster than the internet can actually get there. Now, this made news for a little while. It was kind of like a humorous thing. It's like, the internet is so slow in this particular village that a carrier pigeon is faster to transfer data between a town 50 miles away. So they actually ran this, the internet versus the pigeon, and guess who won? Pigeon. Otherwise, it wouldn't be really a good story. But that was kind of like people were starting to poke holes at it, because it's like, what they did was they took, if you give the pigeon like a USB drive, and that USB drive can hold like 10 gigabytes of stuff, you can put 1 gigabyte or 10 gigabytes or 5 gigabytes inside that hard drive, and it doesn't change the amount of time that it takes the pigeon to go, because the weight is exactly the same. Whereas if you were to do like 1 gigabyte worth of stuff that you're uploading versus 10 gigabytes when it comes to internet speeds, that's a very different thing, because the weight of that is different. So the physical weight for the pigeon is the same whether you put 1 gig or 10 gigs of stuff, but the internet speed is not measured in the exact same way. So you can kind of think of the real life example as like the pigeon. So O of n is linear time, so it kind of grows linearly going upwards, which means that your runtime is going to grow linearly based on what you pass in. So you can kind of see, this is an example of an algorithm that runs on linear time, O of n. So I have a contains method, and the first thing I'm passing in is an array, and the second thing is the value. And what I'm going to do is I'm going to iterate over each one of the items in the array, and if the item is equal to the value, I'm going to return true, otherwise I'm going to return false. So that means that if I give you an array of one thing and one particular value to look for, it's going to take a shorter amount of time than if I gave you an array of 10,000 things and one thing to look for. That time is going to increase based on the input that you give it. You can kind of think of it as more money, more problems. That's what people hear. The more money that you have, generally speaking, not generally speaking, you may or may not have more problems. I find it hard to believe personally. I would like to have more money, but I hear that is the case. You have to worry about bodyguards, and you have to worry about people trying to steal your wealth, and more insurance and things like that. I think it's a nice problem to have when I can afford my jet.
I agree with that.
And the other big one that people need to know, again, so these are the big three that I generally find out in interviews: O of 1, O of n, and O of n squared, which is quadratic time. So when you have a loop within a loop, it's a pretty big of a red flag right away. Sometimes it cannot be helped, but most of the time it can be. Maybe you split it up into 2 separate loops somewhere else. But let's say you have all combinations, and you have an array of 1, 2, 3, 4, 5. All the combinations would be 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 1, 2 and 2, 2, 3, 4, 5, and so on and so forth. And you want to print all of those out inside of one results array. So I have an empty array. I'm going to iterate over each one of the numbers and save that as number 1. And then I'm going to iterate over that same array and save that as number 2. So this one's going to be 1. Number 1's going to be 1 for the first round, and then I'm going to iterate over each one of those numbers, 1, 2, 3, 4, 5. And I have 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5. So the amount of times that my particular code is running is 25 times, or just the squared of the amount of times what I'm putting in. So if I have something, let's say if I have 10 things I'm passing inside of an array, I'm going to be running through this loop 100 times to print out every single possible combination. That's going to be much slower than if you had something more efficient. Big takeaways, and then we'll take a break while I get Chris set up. Searches, when you do any sort of search, going through a hash is going to be faster than arrays because hashes don't keep track of indexes. Whenever possible, avoid nested loops, which are when you have a loop within a loop. I have seen loops within loops within loops within loops for some people's code, and that is really, really bad. So it's kind of like 10 to the 4th power. That's the number of times it may need to go in. And then when you find yourself doing, generally speaking, loops within loops, you may want to consider refactoring because it's not the most efficient way of writing. Sean?
I understand, like, there's tons of nuances to this. Like, for instance, like, an array, if you, like, push or pop, it's not a big deal. But if you slide something on the front of it, the shift or unshift, you have to rewrite that entire thing around. So, like, there's, like, all kinds of weird things that you have to, like, know once you start working. Is that true?
No.
Okay.
9 times out of 10, you don't need to worry a terribly large amount. I have not really needed to worry about the efficiency of my code once I got to my job because I just memorized don't have loops within loops and don't use recursion. And for most companies and for most jobs, that is enough from what I've seen. Chris, do you have anything for that?
Have you guys used Rails yet?
Not yet. That's 5 weeks away.
So I think the one thing, like in Rails, there's an instance of this where you're retrieving, you have these like linked tables, associations, and so everything is fine when you're just looking at one table, but when you start looking at like a thing that points to another thing in the table, and you just do it the simple way, like thing.thing, then you have a lot of those things, and it suddenly just blows up. And so you have to start to think about this a little bit in that case. And there's a Rails statement called includes, which basically says, get everything you're going to get here, and then go look it up, so it becomes an order in problem instead of an in squared problem. But that will come up and bite you as soon as you start to scale up over Rails.